to forge some tighter connections between the two departments, which I think can be a nice thing. Our speaker today is Professor Steffen Baas from the Duke Department of Physics. Professor Baas got his PhD in theoretical physics from the Goethe University in Frankfurt mit Auszeichnung, which I am told means with honors in some form. After he got his PhD, this was in 1997, I suppose. He came to Duke in 1998 as a postdoc, working with Bernd Müller in the nuclear theory group. After that, he spent 2 years at Michigan State University and then came back to Duke in a position that was jointly funded by RHIC, the Japanese Research Institute. And he was affiliated with Brookhaven National Lab, where, of course, the Relativistic Heavy-Ion Collider, RHIC, was churning out data that Professor Baas was interested in analyzing. He came, so he'd been at Duke since 2000. He became the department chair in 2019, but that's not why we invited him to speak today. Just this past year, he was promoted to the title of Arts and Sciences Distinguished Professor of Physics at Duke, and we thought it appropriate to highlight the current trends that are stemming from the work that was the basis for this recognition with the distinguished chair. So since 2000, he's been working on relativistic heavy-ion collision physics, Quark-Gluon plasmas, and hadronization and hydrodynamics, and we're interested in hearing what he's going to tell us today about that. And I will also just add that Professor Baas is a fellow of the American Physical Society and an outstanding referee. So, Steffen, we're looking forward to hearing about quantifying shear viscosity in nature's most ideal liquid.
All right, thank you, Josh, for the kind introduction. I'm very pleased to have the opportunity to talk to you all today. And yes, so I'm going to give a talk about something that many of you may not readily identify as a topic of research in nuclear physics. Hold on. But since this is a colloquium, I'll start out pretty basic to set, the terms and the scenery. And really, since we're talking about nuclear physics and also particle physics, let's briefly review the elementary building blocks of matter. Yes, and you can start out with an ordinary object like a fly. It's made up out of molecules. Molecules are made up out of atoms. Atoms have an atomic nucleus and a bunch of electrons around it. The nucleus is made up out of protons and neutrons, and currently we believe the most elementary constituents are quarks and gluons that make up the protons and neutrons. So in the standard model of elementary particle physics, you have 6 different species or flavors of quarks. You have leptons, and you have gauge bosons that transmit the 4 elementary forces of nature, right? For us, the most relevant force is quantum chromodynamics, which is the strong force that mediates the interactions between quarks via the exchange of gluons. And I should also add that for the ordinary matter that our fly is made up from, you really just need up quarks, down quarks, gluons to create the protons and neutrons, and of course electrons for the atoms and the molecules. All right, now let's go up a few scales to the concept of matter. And the simple form of matter that we can look at is water. And water usually is a liquid, yes. But if I cool water down to 0 degrees Celsius, it forms a solid ice. And if I heat it up to 100 degrees Celsius, it evaporates and forms a gas. And if I would heat it up even further, then at some point, the electrons would dissociate from the atoms, and I would have a plasma, right? Now, temperature is not the only control parameter I have in determining the phase that my matter is in. Pressure is another one. Yes, if I were to boil my pot of water on Mount Everest instead of Wrightsville Beach, then I would find that the water would already boil at 71 degrees Celsius instead of 100 degrees Celsius. So the phases that my matter, water, is in depend both on temperature and on pressure. All right, now for water, that's of course fairly boring. You need a thermometer, a barometer, and a heating and cooling device, and you can figure this out. And this has been done, centuries ago. On the theory side, the way how you can do that, of course, is by evaluating the derivatives of the partition function, right? So phases are actually, the phases of my substance, of matter, are determined by the interactions between the molecules, right? And for water, that would be the van der Waals interaction between the water molecules. Yes. And on the experimental side, as you've seen on the previous slide, I apply heat and pressure to study the phase diagram. On the theory side, I can calculate the derivatives of the partition function and thus can figure out what the phase diagram is. As I said, for water, this is all well known, but if we now go to quantum chromodynamics, the quantum field theory that governs the behavior of strongly interacting matter, quarks and gluons, this becomes a slightly more complicated endeavor. By the way, in the background, you can see a picture of the IBM Blue Gene computer, which is an extension of a computer called QCD-OC, which was the first custom-built computer to actually try to calculate the equation of state of QCD matter. So QCD matter, basically going from water, I'm now going to ask the question, what is the equation of state for the matter that makes up an atomic nucleus? Yes, and it is actually not so far-fetched to ask this question. Yes, we have known from classical nuclear physics that an atomic nucleus quite often behaves like a liquid drop. All right, liquid, just like water. So you can ask the question, what temperature does it take to actually get this nuclear liquid to boil, to evaporate? At what temperature can I get it to a plasma phase? Could I ever freeze it down to a solid? Yes, at what pressure and temperature can I affect all these things? And so it is quite natural to try to ask the question, really, what is the phase diagram of QCD matter? Well, on the theory side, again, I have to solve the partition function and take its derivatives. In order to do that for QCD, I have to use a tool called lattice field theory. Now, this talk is not going to be about lattice field theory, but I have to flash, one historical result of that sort of justifies all the effort that we're putting into this area of research. So lattice field theory, and I'm trying to find my pointer here. Oops. Which I don't find. All right, sorry. So lattice field theory predicts that there will be a phase transition from the matter made up out of protons and neutrons to matter made up out of quarks and gluons at some temperature in the vicinity of 200 MeV. And the way this prediction was done was trying to solve the partition function using the techniques of lattice field theory. And what you see here in this figure is one of the outcomes of that calculation. On the x-axis, you have the temperature plotted. On the y-axis, a quantity which is energy density divided by temperature to the fourth. And the reason why these particular units or these particular quantities were used is that if you go to a statistical mechanics textbook and you try to evaluate the equation of state for a gas of ultrarelativistic massless bosons, you find that the energy density is proportional to temperature to the fourth times the number of degrees of freedom of the system, times the numerical constant. So if I bring temperature to the fourth on the other side, then on the right-hand side, what remains is just the number of degrees of freedom. And so what's really plotted on that graph is the rise in the number of degrees of freedom as I increase the temperature from a temperature in which hadrons, protons, and neutrons exist to a temperature in which quarks and gluons exist as deconfined degrees of freedom, which have a much larger number of degrees of freedom than if I just have quarks and protons and neutrons in a system. And so that happens at a temperature of around 160 MeV. All right, so lattice field theory has basically confirmed to us that there exists this phase of quarks and gluons at a temperature higher than 160 MeV. Now, why are we interested in this phase? Well, turns out that a few microseconds after the Big Bang, actually the entire universe was in this Quark-Gluon Plasma phase before the universe continued to expand and cool down and formed protons and neutrons and then atoms and molecules up to, the heavy elements, the elements and the heavy elements that we see in our universe today. So on the microsecond scale of its lifetime, the universe was in a Quark-Gluon Plasma phase. And if we can explore this Quark-Gluon Plasma, we may conceivably learn something about the early universe a few microseconds after its creation in the Big Bang. All right, so how do we do that? Oh, well, before I go there, this talk is actually not going to be about the equation of state of QCD matter, but about other properties that are associated with matter, transport coefficients. Yes, in particular, shear and bulk viscosity. And shear and bulk viscosity have an easy definition. You write out the stress energy tensor in terms of an expansion in the gradients of velocity. U is the velocity here. And you find that the shear viscosity eta and the bulk viscosity zeta are just coefficients in the expansion of that stress energy tensor in terms of the velocity fields. Yes, and of course you can write down such a tensor pretty much for every theory that you can define. You may now, of course, ask the question, well, if lattice field theory was so good and giving us information about the equation of state of QCD matter, could I use lattice field theory to actually also calculate the shear and the bulk viscosity of QCD matter? Well, it turns out that that's not so easy. Yes, formally, in order to calculate the shear viscosity or the specific shear viscosity, which is the shear viscosity divided by the entropy density of the system, you would really have to take a zero momentum limit in an infinite spatial volume, which numerically you cannot do using standard lattice field theory techniques. So a few research groups have tried heroically to come up with some estimates, but these estimates have error bars on the order of 100% roughly. And that has not changed over the last decade or two. So there has to be a different way how we can gain insight into the transport coefficients of QCD matter. And so this is something that the research community that I am part of has focused a significant part of its effort in over the last 2 decades to learn something about the properties of the Quark-Gluon plasma or QCD matter more generally, and what its transport coefficients are. All right. So how do we study the Quark-Gluon plasma? Can we create a Quark-Gluon plasma? I mean, obviously, we do not want to recreate the Big Bang, but somehow we have to gain some insight into that system. Well, so continuing on our narrative about the viscosities, back in 2006, 3 luminaries in our field actually started posing this question, what can we learn about the shear viscosity of the Quark-Gluon plasma, and how can our knowledge regarding the shear viscosity of other systems can help us inform us about what to expect from the Quark-Gluon Plasma. And so that was a seminal paper which appeared in the Physical Review Letters. And the key plots you see on the screen, which shows the specific shear viscosity, that is shear viscosity divided by entropy density, for helium, for water, and what was then known for strongly interacting matter. Not quite the Quark-Gluon Plasma. Well, there is a Quark-Gluon Plasma curve on there, but that's basically calculated in a particular limit of perturbative QCD, which breaks down once you go below a temperature of a few hundred MeV. So it essentially breaks down in the most interesting temperature range for the Quark-Gluon Plasma, close to the phase transition from regular hadronic matter to quark-gluon matter. And the dashed line on the left side of that figure is for pions, which is, the simplest form of hadronic matter, bound state of a quark and an antiquark that you can find. But certainly a gas of pions is not really a good model for QCD matter in the confined phase, since you have many other bound states, kaons, protons, neutrons, hyperons, cascades, omega baryons. So the zoo of particles that are bound states of quarks and gluons is comprised of over 100 different particles, and the dashed line here in this figure only has one species. All right, fast forward to 2019, and the story I'm going to tell you today is the story of this figure, where we have been able in our group to quantify the specific shear viscosity of the Quark-Gluon Plasma and basically put the curve on the plot that's missing in the 06 PRL by China, Kapusta, and McLaren. So this is more of a decade of work by multiple research groups that culminated in us being able to do this analysis. It's a cooperation between theory and experiment, and it's a significant investment by the funding agencies that have kept us going for more than a decade while we were working on this problem, and also have supported us with significant resources that we need for the computation of this quantity. All right, let's take a step back and answer the question, how do we create a Quark-Gluon Plasma in this day and age? Obviously, we do not want to recreate the Big Bang. That would be very unpleasant for us. But what we want to do, of course, is we want to create a small amount of Quark-Gluon Plasma that we can study in the lab. And the only way to do that, or more generally speaking, the only way to heat and compress QCD matter under controlled laboratory conditions is by colliding two heavy atomic nuclei. And the best facility in the world, or let's say the most powerful facility in the world to do that right now, is the Large Hadron Collider at CERN in Geneva. This is a huge accelerator, 27 kilometers in circumference, which passes underneath the Swiss-French border. And it has, was not custom built to study the Quark-Gluon Plasma. This facility was built for the discovery of the Higgs boson. It was very successful. It did discover the Higgs boson. But it can also study the Quark-Gluon Plasma, since the Large Hadron Collider is flexible enough not only to collide protons, but also to collide lead nuclei. And while the proton-proton collision system is fantastic when you want to study elementary interactions and the creation of exotic particles in the physics beyond the standard model, it really doesn't create a lot of matter. Yes, if you want to create matter, bunch of quarks and gluons that interact with each other, that allow us to define a temperature for the system, then I need as big a volume of hot and compressed QCD matter as I can possibly get. And I do that by colliding the heaviest nuclei I can stick into my accelerator. Yes, and the Large Hadron Collider can do that with lead nuclei. All right, there are 4 experiments at the Large Hadron Collider. One of these, ALICE, is custom built for the study of the Quark-Gluon Plasma. It is a collaboration of over 1,000 scientists from over 100 institutions. the device is huge, 26 meters long, 60 meters high and wide. It weighs 10,000 tons. And it is actually still a lot smaller than the Atlas and the CMS detectors that were used for the discovery of the Higgs boson. Anyhow, ALICE is really optimized for the measurement of the collisions of lead nuclei. And I'll show you in a minute why this optimization makes sense. So what you see here in this picture is the visualization of an event recorded by Atlas of a proton-proton collision. And what you see here is about 24 tracks of particles that come out of this proton-proton collision. Among them, highly energetic particles that mark this event as having produced a Higgs boson that subsequently decayed. Yes, but what you can see is that the track density is not particularly high, and so the tracks are easily identifiable and assignable to particles, pions, protons, muons, electrons. And what the challenge is for these experiments that we're searching for the Higgs is that they have to record many of these events, most of which are entirely boring, to sift out the few exciting events that resulted in the creation of a Higgs boson. Well, so that is not the challenge when we are colliding lead nuclei, yes, in order to create the Quark-Gluon Plasma. There, every event is interesting, but every event looks like this. So the track density goes up tremendously, since now you're colliding 208 protons and neutrons onto 208 other protons and neutrons. You need a very different detector to handle those kind of track densities and reconstruct every single particle so that we can characterize what happened in this collision of the two lead nuclei, how the protons and neutrons of the two lead nuclei dissolved into quarks and gluons, how they interacted, what kind of temperature we achieved, and how the system then disintegrated to result in those tracks that you see here on screen. And so that is what the ALICE detector does best, is to record all these tracks and then characterize them as what kind of particles came out of the collision. All right. So how do we make sense out of this huge mess of particle tracks? How can we associate these digital images with a quark-gluon plasma, with its temperature, with its transport coefficients like the viscosity? For that, you need to develop a theory. In our case, we're going to use transport theory to develop that theory, or develop a model of what happens during the collision that we can connect to the experimental observations. Transport theory can take on many forms. You can develop a microscopic transport theory based on a transport equation called the Boltzmann equation. That would essentially describe an ensemble of particles that interact only through scatterings, but you are able to really describe the trajectory, the momentum, and the position of every particle and track it through the sequence of collisions each such particle undergoes. In the opposite limit is fluid dynamics. If you have too many particles in the system that it doesn't make sense anymore to really look at individual particles, you can discretize your system into cells, fluid cells, and just solve basically differential equations for the evolution of moments of the particle distribution, like energy density, as an example. And there are other types of transport equations, like a Large Hadron equation that you can use in special instances when you're only interested in very special particles that migrate or diffuse through a heat bath, for example. You can also develop hybrids, combinations of fluid dynamics and Boltzmann transport that are applicable over a wider range of particle densities and temperatures. Now, one commonality, no matter which type of transport equation you use to develop your computational model, is that each of these models has parameters that govern the physics that you put in. And these parameters will act as a representation of the information that you can extract from comparing your computational model to the experimental output that you have received from the particle detectors. So here is a visualization of a fairly state-of-the-art computational model for describing a collision of two heavy atomic nuclei. What you see here is the two nuclei as they are approaching each other. They are approaching each other at nearly the speed of light. And so they are Lorentz contracted, and you can envision the system really as two pancakes colliding. All right, so after the collision starts out, we form a Quark-Gluon Plasma, and our fluid dynamics turns on. Fluid dynamics, then you see the different contour lines with the different temperatures of the system. A Quark-Gluon Plasma was formed. Here, one temperature surface is missing, but once the Quark-Gluon Plasma decays, you form an ensemble of particles, bound states, hadrons, quarks and gluons, protons and neutrons, pions, kaons, and so forth, that continue to scatter off each other until the density of the system is so minute that the particles stream into your detector. And those are the tracks that you observe. So the tracks are really the tracks of the particles that come out after this entire collision evolution is over and your Quark-Gluon Plasma has decayed. Here are a few snapshots, and associated with it is a time scale. And this time scale already tells you one of the challenges that you have in studying these systems dynamically. Yes, we have nuclei approaching each other at 99.99% speed of light. And the entire collision process is over in about 10 to the negative 23 seconds. Yeah, so the lifetime of the Quark-Gluon Plasma is on the order of 10 times 10 to the negative 23 seconds at most. That is a time scale that you cannot resolve with any experimental apparatus. So the only thing that you observe really is the final state of the system, the particle momenta at the far right of our visualization, which is the point where the system is so dilute that it has ceased to interact, where it is frozen out. So the way we model that computationally is that we start out with some kinetic theory for the early times that are out of equilibrium. As soon as the Quark-Gluon Plasma has formed, we utilize viscous fluid dynamics. I should say relativistic viscous fluid dynamics. And as soon as the temperature of the system goes below the critical temperature for the existence of a Quark-Gluon Plasma, and we are back in the world of bound states of quarks and gluons, hadrons, then we switch over to a Boltzmann transport that allows us again to describe the evolution of the system without relying on equilibrium assumptions that are inherent to any kind of fluid dynamic approach. The principal challenges in studying our system experimentally and also in terms of computational modeling is that the timescale of the collision process is too short to resolve experimentally. The length scale that we are probing during the collision is also too small to resolve experimentally. And you have this property of QCD called confinement, which tells us that you cannot ever observe a single free quark or gluon in nature. You can only observe quarks and gluons as so-called color-neutral bound states. So experiments do not observe quarks and gluons directly. They can only observe basically the ashes of the decay of the Quark-Gluon Plasma, which are bound states of quarks and gluons like protons, neutrons, kaons, pions. So what you need if you want to take a look at the time evolution of the Quark-Gluon Plasma is a computational model for the time evolution of the collision that allows you to connect what you observe at the very end to the brief time period in which a Quark-Gluon Plasma was formed and evolved before it decayed. Yes, and that's what these computation models are all about, is to provide you with a simulation of the full process, and the final output of that simulation can then be compared to the experiment. And if I get a good match, then I can be bold enough to state that, all right, if my simulation matches at the very end to the experiment, then I can sort of trust what my simulation did in its earlier times and ask the question, what type of Quark-Gluon plasma did I need in my simulation to actually have that match at the very end? Okay, so in simpler words, what I need to do is I need to be able to compare the output of my simulation with the output of the experiment. And if I'm successful, then I can extract knowledge out of my simulation. So how do we do that? So the experiments measure particle tracks, and these particle tracks are then identified as particles that have momenta and mass and charge. And then I use that information of a particle list with particle momenta and masses and charges to construct observables and bin them in histograms, like a momentum distribution of all the particles, or an angular distribution for the emission of my particles, or just a number distribution. How many particles did I get out of my event? Yes, my simulation can do the same thing. Yes, the final output of my simulation is also a list of particles. So I can use that particle list, just like the particle list that I get out of the experiment, to calculate these observables, these data reductions that my experiment calculated. And then I can compare the two, and see whether I get a match. And in the old days, what I would just do is I would develop some computational model, guesstimate a few parameters, run the model, calculate my observables, do the comparison. And if I got lucky, then I had a reasonable agreement, but I would never really know whether my parameters were the real optimal parameters or whether I was just ever so slightly off, or whether I was actually off by a fair bit. Yes. And if I only have one or two parameters to vary, then obviously I can do some kind of least square fit. However, as we shall see, we are here in a situation where that doesn't work anymore. Okay, why are we in a situation where that doesn't work anymore? A good computational model these days has about between a dozen or 2 dozen parameters. Good experiment, creates a list of thousands of particles per collision event and is able then to calculate dozens of different observables from those particle lists. You can have momentum distributions according to different particle species. You can have particle yields sorted by centrality, which is a measure of the impact parameter of the collision. You can have angular correlations. You can have Bose-Einstein correlations among your particles. You can have all sorts of other correlation measurements, right? As it now turns out, I can calculate all of these in my computational model. And what I find is that pretty much every one of my parameters affects the value of multiple different observables that I can calculate. So there is no way that my system factorizes that I can say, all right, I only have to look at one observable and I only need to tune one parameter because that one parameter is only sensitive to that one observable. That unfortunately does not work. I have a large number of interconnected parameters with non-factorizable data dependencies. My data have correlated uncertainties. And so I need to develop optimization techniques that allow me to tune or to calibrate all of my parameters simultaneously to a large high-dimensional data set that encompasses all the knowledge that I can gain out of these experiments. This is a general problem. It is by no means specific to heavy-ion physics. Climate scientists have the same problem with their climate models. Yes, cosmologists have the same problem with their cosmological models. Yes, gravitational physicists have the same problem when it comes to gravitational waves. This is good news. It means that the techniques that we will use to solve this challenge have been actually developed by Bayesian statisticians and have been used in other domains of science. And so we don't have to reinvent the wheel. So what do I mean? So what we have to do is a Bayesian analysis. And let me briefly explain what we mean by that. And so I want to come back to our general idea of a computational model that relies on a set of physics parameters to vary its features, right? And so these parameters in my model are a representation of the information that we can extract from comparing the model to the data. In the old days, I would define my parameters, I would guesstimate their values, I would run my physics model, my simulation, and I would then compare to the experimental data. That could be quite tedious if I have a lot of parameters or a lot of data to compare to. In a Bayesian analysis, I'm going to turn that error around, and I'm going to use the entirety of my experimental data, run my Bayesian analysis through my physics model to simultaneously extract the values of all parameters of my model, including their uncertainties. Yes, so that's the power of the Bayesian analysis, that I can simultaneously calibrate all model parameters. I will know which parameter values best describe the data, and I will also get the uncertainties that are associated with that extraction. Yes, there is no way, since my experimental data always have uncertainties, error bars. Yes, there is no way that any kind of physics model would be able to say, this is the precise value of whatever, the shear viscosity. It always has to come with an uncertainty. Yes, any kind of extraction contains an uncertainty, and the Bayesian analysis allows me to estimate those uncertainties as well. All right, and just an example on where a Bayesian analysis was tremendously successful was the LIGO observatory for the discovery of gravitational waves. Yes, many of you have seen at least a figure on the left, which are the wave patterns recorded by the two LIGO observatories. Now, what LIGO did actually was that they had a computational model for the waveform that they should expect for the merger of two neutron stars in an event. Yes, and what they had to do was they had to do a Bayesian analysis to tune that computational model for the neutron star merger to the signal that they actually measured when such an event came through. And the output of that analysis weren't two exact masses for the two neutron stars. The output were probability distributions for the two masses. And those are the histograms that you see on the right-hand side on the two axes. Yes. So that's really the hallmark of a Bayesian analysis, is that what you get out are not specific values for your parameters, but probability distributions for the parameters in your analysis. All right. So the setup of such a Bayesian analysis can look somewhat intimidating. You have the model parameters, which are the properties of the system that you wish to learn about. You have your physics model, which is the simulation or the theory you have developed to describe a physical process. And you have your experimental data. But then you need this analysis machinery to apply what's called Bayes' theorem and actually make it all work to extract your parameters in this analysis. And we will even take an extra detour called the Gaussian process emulator. And I will walk you through every single box of this analysis to show you how it was done. Okay, let's start out with the physics model. This is something that I've already talked about. Based on transport theory, we have developed a computational model for the time evolution of a heavy-ion collision. We are starting out, we are using essentially a model that is made up out of 3 components. One component to set up the starting point for our hydro. Fluid dynamics is nothing but a set of partial differential equations. In order to start a fluid dynamical calculation, you need essentially an initial value. Yes, an initial Quark-Gluon Plasma distribution, which you then dynamically evolve through the fluid dynamical equations. This is done with a parametric model that we call Trento. It was developed in Duke by 2 of my grad students over the last 4 or 5 years. We use that to start out fluid dynamics. The fluid dynamical code that we use was called Vishnu, and was developed by colleagues from the Ohio State University. It takes as input, for example, the equation of state of QCD matter calculated from lattice field theory. Yes, that is an input that in itself, required millions of CPU hours and was done by a research group in Bielefeld and Wuppertal in Germany, a collaboration called the Hot QCD collaboration. Yes, and then once fluid dynamics, exits its realm of applicability, we use a Boltzmann transport called URQMD to evolve the now hadronic system up until the point when our particles cease to interact and represent and act as a good representation of the tracks that the experiments measure in the lead collisions at the Large Hadron Collider. Yes, so these are fairly involved computational models. Altogether, they require about 15, 16 parameters to run. These are not computer codes that you write in an afternoon. Vishnu is the product of perhaps 4 grad students working 5, 6 years to get the model to the point where it is. URQMD required 4 or 5 grad students working 6 years to come to the point where it is today. And Trento, that was 2 grad students working 3 years. And so this research relies a lot on teamwork and on collaboration among different research groups at different universities, and also on the willingness of these research groups to share the fruits of their labor. And all of these codes, by the way, are nowadays open source, so that people can play around with them and build on what has been created to improve them. Okay, so model parameters. I will not go through all the 15 model parameters, but I will highlight a few that will be relevant to us. So the model parameters I talk about are the ones that we are going to vary in our analysis to figure out what the optimal values are coming out of the Bayesian analysis, right? And so these are the physics quantities that we can learn something about. One parameter, you can call it a nuisance parameter, is the temperature at which we switch from a fluid dynamic evolution to a Boltzmann transport. There is physics in this parameter, given that fluid dynamics relies on the assumption of local equilibrium, and Boltzmann transport does not. So this parameter will inform us at what temperature our system is prone to run out of local equilibrium. We need a few parameters to nail down the initial energy density deposition that forms a Quark-Gluon plasma, basically the initial condition for our fluid dynamical evolution. We will need a few parameters to come up with a general functional shape of the specific shear viscosity. There is no physics in this parameterization. It's a simple power law ansatz. And we will just see, what shape comes out after the Bayesian analysis has done its job. As likewise for the specific bulk viscosity, the only prior knowledge that we put into our parameterization is that we assume that the specific bulk viscosity has a peak. That is quite reasonable. Usually specific bulk viscosity should peak at the phase transition temperature of a system. All right. Now, what type of data do we use from the experiments? That's of course crucial. You need data that allows you to access the physics you're interested in. So, and then picking the right data is not easy. Let me give you an example about the type of data that we focused in on our analysis and that provided us with a leg up in this endeavor. When you collide 2 nuclei in a particle accelerator, these nuclei will never directly collide head-on, or very rarely will do so. In most cases, these nuclei will collide with a certain offset, an impact parameter. And so what you're heating up in the collision is really not the full extent of both nuclei. What you're heating up is the overlap area between the two nuclei, basically the collision zone. Yes, and if I assume that my two nuclei are sort of circular roughly in their geometry, then the overlap area will have the shape of an almond or of a football. Yes, so now this almond is highly compressed. That's my Quark-Gluon Plasma. Yes, and it's highly compressed. It wants to expand. This system, no matter whether the Quark-Gluon Plasma or any other kind of strongly interacting matter, will of course expand most easily normal to its surface area. Yes, so this system will expand predominantly along its short axis. Yes, and it will expand not so much along its long axis because there's no surface pointing in that direction. Yes, so what you can expect if you create a highly compressed system that's the shape of this almond is an anisotropic emission of particles, which we refer to as elliptic flow. And this particular angular distribution, now you can sort of, you can plot that in terms of the angles of the particles that get emitted, and you can do a Fourier decomposition that then informs you, how elliptic this expansion was. And colleagues of mine at the University of Washington many years ago actually discovered that this emission pattern, this angular correlation in the emission is very sensitive to the specific shear viscosity of the system if you model it with viscous fluid dynamics. So what you see in this figure on the right-hand side are 4 curves and a number of data points. The data points by now have much smaller error bars, but I've taken the historical figure. And the 4 curves that you see are 4 different fluid dynamical calculations with different values of the specific shear viscosity. And you can clearly see that, and then on the y-axis, you have the Fourier coefficient that describes this anisotropic emission of particles. And on the x-axis, you have a measure of the impact parameter of the system, so sort of a measure of the eccentricity of the almond. And you can see there's significant sensitivity in the fluid dynamical calculation, depending on what specific shear viscosity you dial in. Okay, so that discovery was a stroke of luck for us because it gave us a measurement, this azimuthal anisotropy, that we knew was sensitive to this particular transport coefficient, the shear viscosity that we were interested in. All right, now elliptic flow is a phenomenon that is by no means just observed in relativistic heavy-ion collisions. What you see here is the release of lithium atoms out of a magneto-optical trap. And these lithium atoms are in a magnetic field that dials in their interaction such that it's maximally strong. Yes, and what you can see is that the system exhibits a very strong elliptic flow. Yes, this is an experiment that was done by John Thomas and collaborators here at Duke University back in 2002, and generated a lot of excitement in a variety of communities, since it showed that ultra cold quantum gases can be used as model systems for a whole slew of other physics systems that may be harder to access. Yes, this is a tabletop physics experiment. That was done in a simple lab in the sub-basement of our physics building. And it shows you phenomena that we would also observe at a much higher level of effort using a $1 billion collider and a 10,000-ton experiment with over 1,000 scientists involved. Yes, so these experiments were incredibly valuable for the discussion of the science, and very, very exciting. All right. So here is now the actual data that we will be using for our comparison. Apart from these Fourier coefficients that denote the anisotropic expansion of the system, we also look at the average transverse momentum of different particle species. We look at the number of particles being emitted for a given impact parameter or centrality of the collision. So we have about 50, 60 different individual data points that we will be comparing to. And the experiments measure a lot more other data. What we were focusing on in this particular analysis was mostly data that the experiments could measure with very small uncertainties. Yes, we wanted to reduce the error bars as much as possible. Okay, now let's come to the mathematical and computational tools that we needed to use in order to get this analysis going. All right, so I have a computational model. This model relies on about 16 parameters. Usually, you would argue, all right, I have a bunch of parameters. Why don't I just vary all these parameters and study the response of my model to see how my model behaves? And by varying the parameters, I'll gain some insight, on how the model behaves. And then I can sort of tweak my parameters to, describe the data. If that's the basic idea. Okay, so I have 14 model parameters. My experiments can characterize the impact parameter, which is a measure for the eccentricity of my element shape in 9 different categories or classes. And if I now want to vary my parameters, I would say, all right, let me pick 20 different values for each of my parameters. That should give me a good feeling on how my model responds to the variation of each of these parameters. All right. So with 14 parameters, that means I need to now evaluate 9 times 20 to the 14 points in my parameter space. Unfortunately, my model contains probabilistic components, right? It's quantum matter. So I can't just model one collision. I need to repeat that process 10,000 times and average over the outcome in order to construct robust observables. Okay, so this means that if I want to scan my parameter space, I'm now at 10 to the 18 events that I need to calculate. Each of these collision events, and you saw the visualization for one of those, requires about 1 hour CPU time. So I need 10 to the 18 hours of CPU time to study my parameter space. That's 2 billion years of 100% use of the Titan supercomputer at Oak Ridge. Yeah, that's not going to work. And then I'm not done, right? After I've done that, I still need to start, a Markov chain Monte Carlo to find out which of these points that I have calculated in my parameter space actually optimally describes the data. So this was the dead end that our community found itself in for many years, and led a lot of people to actually give up on actually doing these kinds of research projects. So the challenge really is that one needs to find techniques that cut down the required CPU time by at least 10 orders of magnitude without diminishing the sophistication and the quality of your computational model. And that's where our friends from the statistical sciences come in, because they have developed a technique based on Gaussian process emulators that allows us to do just that. That I would say was probably the biggest breakthrough for us, was the use of Gaussian process emulators to make this from an impossible calculation to a feasible calculation. So what's a Gaussian process? Yes, it's a stochastic function that maps inputs to normally distributed outputs. They're fully specified by a mean and a covariance function. And you can use them as to do a non-parametric interpolation of your physics model between points at which you have actually evaluated your physics model. Yes, so think of these Gaussian process emulators as a clever way of interpolating your model between points where you have actually evaluated it. Yes. This makes Gaussian process emulators, broadly speaking, a part of machine learning. Yes, so what we have been doing here is actually using machine learning techniques to help us get a leg up in our problem. And one of the big advantages of these Gaussian process emulators is that they reproduce with 100% accuracy my physics model at the points where I've trained them on. And in between those points where I'm interpolating, they will not only give me a reasonable interpolation, but they will also give me a measure of the uncertainty of the interpolation. So if I'm far away from my training points, I will have a larger uncertainty, and if I'm closer to my training points, I have a smaller uncertainty. And that will be incredibly useful for us to sort of make good use out of these GPEs and assess how good the interpolation actually works. The other advantage of these Gaussian process emulators is that they are very, very fast once you have concluded the training. Yes. And so here's the clue. Instead of evaluating now my model at 10 to the 18 points, yes, I will come up with a much sparser collection of points at which I evaluate my physics model. And the sparse collection of points, roughly 500 points, will be determined by what's called a Latin hypercube. This is an algorithm for generating semi-randomized space-filling points that avoids large gaps and tight clusters in these points, but they're randomly distributed in my 15-dimensional parameter space. Yes, and when I want to train these Gaussian process emulators, I need about 10 endpoints, n being the dimensionality of my parameter space. So if I have 15 parameters, then I could get away with as little as 150 points at which I evaluate my physics model, train my Gaussian process emulators on, and then use my Markov chain Monte Carlo on the Gaussian process emulators instead of the physics model itself. Yes. So I go from 10 to the 18 to 150 or 500. 10 to the 18, 500. That's the gain or the big advantage of using this technique. So we were, doing this on the cautious side. We set up a Latin hypercube with about 500 points. We still need to calculate 10 to the 4 events per each point. So we end up with about 35 million events. It's not a small number, but it's feasible. And then we use the Gaussian process emulators to interpolate between these points to conduct our analysis. All right, 35 million events. How do we get those? We go to a facility called NERSC, National Energy Research Science Computing Center in Berkeley, California. They have a machine called Edison, which is a cray with about 5,000 nodes, each of which has 24 cores. We developed a workflow that allowed us to run a job on 1,000 nodes simultaneously. So we were running on about 48,000 cores simultaneously. And so our entire model design with 30 million events, we ran through in one day. Yes, now this does not come for free. You have to apply for allocations at NERSC, and we burned through about 1/3 of our annual allocation in one day just to conduct this analysis. So you have to make sure that you don't screw up, otherwise you're toast. But it is something where we went from 2 billion years of CPU time to one day. So that was sort of the computational gain that we got out of using these Gaussian process emulators and machine learning in order to address this problem. All right, what does Bayes' theorem actually say? So Bayes' theorem relates something which is called the posterior probability distribution, that's in red, to a likelihood function, that's in green, and a prior probability distribution, that's in blue. Prior is nothing but the initial knowledge about your parameters that you may have. Yes, for example, I mentioned that for our bulk viscosity parameterization, we assumed that the bulk viscosity would have a peak somewhere. That is prior knowledge. Yes, it's an assumption, but it's an assumption we are confident in, so that's what we call prior knowledge. The likelihood function, figuratively speaking, that is a measure of the distance between your model output and the experimental data that you're comparing to. Yes, so the closer your model output observables are to the experimental data observables, yes, your likelihood function will give you a measure for that. Yes, think about this in very, very simplified form, as the norm of a vector. And the vector is the distance between the two in parameter space. And the posterior probability function basically will contain all the information we want, namely the probability distribution for all the parameters that we calibrated on. And I'm going to show you now how this looks like. So first here, a picture of what we call our prior. What you see here is in black experimental data, our flow cumulants, the average PT of different particle species, and particle yields as a function of impact parameter. You see also on your screen something that looks like bands, yes, and in different colors. So these are not bands. This is a collection of individual colored lines. Yes, as a matter of fact, each color in each figure, these are 500 lines. These are the lines at which we actually evaluated our computational model fully on the computer. And that is sort of the input into our Gaussian process emulators, where the Gaussian process emulators sort of learn, for what values of our parameters are we going to get, what kind of model response in terms of describing the observables. Okay, so, and as you can see, in the range that we ran our computational model, we are sort of covering the experimental data, but it's fairly broad since, there's no optimization done at this point. After we've trained our Gaussian process emulators and we run through a Markov chain Monte Carlo, which is nothing but a random walk in parameter space, to find the optimum value of our parameters, yes, that process is called calibration. This is the outcome. So this is now at the end of our calibration, after our Markov chain Monte Carlo has converged. Yes, this is how well we are able to describe the data. And again, these are not lines, but these are, sorry, they're not bands, but these are individual lines drawn from the probability distributions for our parameters. And you can see sort of the band nature gives you a measure of the uncertainty that remains in our calculation after we have calibrated our parameters. By the way, what statisticians call a Markov chain Monte Carlo is very similar to what physicists call a metropolis algorithm. Yeah. All right. So how does our posterior output look like? What is the result of our analysis? And I'm going to speed up since I know that I'm running out of time. What you see here is the full posterior distribution. In the diagonal, you have the probability distribution for every single parameter in our analysis. And in the off-diagonal elements, you have the pairwise correlations among the different parameters. So for most parameters, you see that we get nicely peaked distributions, which means that our calibration was able to really zone into, basically constrain the parameters in our simulation and find actually good constraints. But you can also see a few parameters where there is no peak. Yes, and that essentially means one of two things. Either this parameter is not really relevant for the physics that we wish to describe, or you could also argue that the data that we compare to just doesn't provide us with sufficient information to constrain that particular parameter. Either way, that is also very, very, very useful information to have. And based on these values of the parameters, we can now extract physics. And I will talk a little bit about that in the next slide. There's way more information on this slide than I could ever describe in a colloquium. But I want to focus on the viscosities, as in particular on the shear viscosity. So what you have now here in the top frame is the specific shear viscosity that we extracted with an uncertainty band. And you also see the three parameters that that go into that determine the shape of the shear viscosity. Yeah, so that's really the key of or the core information that you need in order to get that uncertainty band for the shear viscosity. Same for the bulk viscosity. It was a 3-parameter function, but you can see that the uncertainty band is a lot larger. And that is mostly due to the fact that there is at least one parameter that we cannot constrain at all in our analysis. Yes. All right. So I'm going to skip forward to come to conclusion. I will just, while I'm skipping forward, I'm going to mention 4 things that you can do in order to validate this type of analysis. Since I've used a lot of different tools from statistical sciences that are not particularly intuitive for physicists up front, there are certain things that you can do to convince yourself that you're doing the right thing. And there are keywords that you can ask me about in the discussion. There is a validation aspect for the Gaussian process emulators. There is the explicit model calculation where you pick the highest likelihood parameters, run them through your model, compare that to the data to see whether actually your model describes the data. There is the predictive nature that you now calculate observables that you have not calibrated on and compare those to the experiment to see where you are. And there's something called the closure test that you have to do to determine whether your analysis actually sort of is reversible. Yes, whether based on your analysis, you can get back what you put in the first place. Okay, so I'm going to summarize. I have talked initially about transport theory and that we created computational models for the description of heavy-ion collisions, because only through these computational models can we make a connection between the very short-lived small Quark-Gluon Plasma droplet that is being created in these collisions and the particle tracks that you measure in your experiments. I have talked about the different components of a Bayesian analysis that you have to do in order to constrain the parameters of your computational model in order to extract insights. And I've shown you that we were able to actually extract through this model to data comparison the specific shear viscosity of the Quark-Gluon plasma, which if you compare it to all other specific shear viscosities that we know of, is actually the lowest of any known substance that we have, right? So this is the most ideal liquid that we can create is this Quark-Gluon plasma. I should add that we are by no means at the end of our journey. We can add more data to our analysis that will allow us also to establish whether that shear viscosity has not only a temperature dependence, but perhaps also dependence on baryon density, chemical potentials. We can look at different collision systems to generate improved understanding of the initial state and on when equilibrium assumptions start to break. We can look at hard probes, jets, and heavy quark observables that are governed by their own transport coefficients. And nothing in my Bayesian analysis really relies on a particular physics model. So if somebody says fluid dynamics is not so great, I want to use a full kinetic theory from the beginning to the end, you can do that. Yes, you can do exactly the same analysis. You just use a different physics model with a different set of parameters and rerun the analysis. And that is certainly something we're interested in doing. This work has been sponsored by the Department of Energy, the National Science Foundation, the Open Science Grid, NERSC, and SAMSI. I would like to highlight, in particular, the grad students who have done all this, Jonah Bernard and Scott Morland, who are both co-authors on the Nature Physics paper, Wai Yao and Ying Ru, who were working on jets and heavy flavors, my research scientist, Jean-François, who is holding the group together, my collaborators in the statistical sciences, Professor Robert Walpert and Jay Coleman, who is now an analyst for the LA Dodgers. You can already tell that most people who work on this research, due to the know-how in machine learning that they acquire, there are a lot of temptations to go in the industry and apply this knowledge to real-world problems, no matter whether it's home improvement, finance, or pharmaceutical development. Of course, also the Ohio State group needs to be mentioned, who developed the fluid dynamical calculation and some statisticians with whom we worked about 10 years ago to develop the framework. All right, I'm done. Thank you very much for your patience, and I'll be happy to take a few questions.
Okay, thank you. So let's give them an applause for the next 10 seconds or so. Make sure to mute after you're done applauding. Okay, so let's, by raise of hands, let's start with the students. If any students have questions. Postdocs? Okay, Ron Malone, go ahead and ask your question.
Yeah, thank you. Dr. Bass, great talk. I have a question. So working at Tunnel, there's some work on a Compton scattering experiment with Bayesian analysis, and they kind of went the other way to look at their theory and determine what parameters in an experiment would yield the largest sensitivity to their model parameters. Are you able to use your tools to do that and maybe select different observables, or perhaps you've already done that?
Yes, absolutely. So the way you can look at it is, remember I talked about that some of my parameters were well constrained. You know, we had a nice, you know, peak-shaped distribution, but for other parameters, we didn't get that. Yes. And what we can do now, of course, is we can use different observables and see how that affects the posterior distributions I get for my parameters, right? Or we can be not so radical. We can just, you know, add one more measurement to the analysis and see how that affects the shape of my parameters. But then suddenly one of the parameters that is not so well defined suddenly gets or something. So there's a lot we can learn by interrogating the analysis in terms of what happens if I add or take away data, yes, measurements on what the outcome of the analysis is. Yes, I can give you one example. Let's see. All right. So if you look here at this particular one, this parameter is the temperature at which we make the transition from fluid dynamics to Boltzmann transport. And we at one point redid our analysis, but instead of using the mean transverse momenta and multiplicities of identified particles, pions, protons, kaons, we took out that information and instead just used charged particles. So we basically averaged over these three particle species. And what happened is that peak totally went away when we did that. So by this, we learned that looking at identified particle species was crucial for us to determine when our system runs out of equilibrium.
Okay, thank you.
Okay, gotcha. I think we're done with students. I don't see any other students. So gotcha, why don't you go ahead and ask your question?
Hi, so thanks for the great talk. I really enjoyed it. I think you had, you mentioned it in your very last slide, but I was wondering whether you can, or are you planning to apply this whole machinery to small systems like PA or even high multiplicity PP, and finally answered the question whether hydrodynamics applies to these small systems, and or compare with the alternative explanations.
Yes. So yes, we plan on doing that. As a matter of fact, we already have a follow-up paper out where we analyzed at 1 beam energy proton lead and lead at the Large Hadron Collider. However, what we did there was that we focused on very high multiplicity proton lead events. So it turns out that when you're at the Large Hadron Collider, you can get proton lead collisions with over 100 particles in a final state. That's a significant number, yes. And with over 100 particles in a final state, the assumption that you still have a small droplet of Quark-Gluon Plasma is not so bad. Yes. Now, what one would need to do in order to learn when this particular fluid dynamical picture breaks down is one would really now have to vary the multiplicity in these small systems to go from 100 particles in the final state to 50 to 20 to 10. And at some point, clearly, it does not make sense anymore to think fluid dynamics. And so that's something that we still need to look at. One way to go about doing this in the context of Bayesian analysis, of course, is to have a competing physics model, perhaps a full kinetic theory like a parton cascade, and run that for the small systems, and then do a Bayesian analysis on this, and then compare the output of those two Bayesian analyses. Yeah, so in each case, you will get a posterior distribution, and you can use techniques like calculating a base factor, which is a quality measure for such a posterior distribution, in order to determine, perhaps which of your physics models has performed better in the analysis.
Okay, thank you. Julietta, why don't you ask your question?
Thank you for the very clear talk. I think I have a somewhat related question to what you were just saying. So if your physics model is missing some elements, what does that look like? Is there a way to see that in the results here, or will the results always, assume that the physics model is correct and slot the data in to fit it as best they can?
All right. Yes. So what's going to happen, of course, is that at some point you're going to get tension between your model output and the data, right? And the tension will either manifest itself in, for example, here you see that the mean PET for the protons is somewhat over-predicted in this particular calculation. Yeah, so that's not bad, right? I mean, overall, the model is doing very, very well. But you can see there is some tension developing there. And if your model gets worse, then of course, you will see more disagreements, or you will see bigger uncertainties. Yes, because then the Bayesian analysis is going to try to sort of shoehorn your model still to the data, and it can only do that by increasing the uncertainties, the uncertainty bands, yes, in order to make it work. And so that's one way you will start seeing that your model is not performing so well. The other way of seeing that something is off with your model is if you just look at the posterior distribution and you have a lot of parameters that you are not constraining very well. That also speaks to your model not being good, since there is a lot of either useless information or just noise in the model.
That makes sense.
Thank you. Any other questions?
Hi, Rico. I can't seem to raise my hand because I'm.
Okay.
But I did have a question. I'm wondering if what it would mean to have an ideal fluid. So we have fluids, super fluids that flow viscosity free, but that's not the same thing as saying eta over s.
Yeah.
And so what does the low value of that quantity tell us about the QGP or about QCD?
All right, so if you look closely at this figure here, you will see that there's this line drawn with a value of 1/4 pi. Is that visible?
Yes.
Okay, so the question was posed by some of my colleagues whether there is an absolute lower bound to the specific shear viscosity that a quantum field theory like QCD could possibly have. Yes, and unfortunately, you can't really calculate that lower bound that easily for QCD. It's too complicated a theory, but you can use string theory. Yes, and there the ADS-CFT correspondence to calculate a lower bound for a field theory that's called n equals 4 supersymmetric Young-Mills. And that's a theory that has some features that are very similar to QCD. And so theorists have often used it as a model for QCD, even though one has to be careful because that theory does not have a phase transition. And for an n equals 4 supersymmetric Young-Mills theory, the absolute lowest value that the specific shear viscosity can have is 1 over 4 pi. And when we started making these analyses about what is the value of the specific shear viscosity of the Quark-Gluon Plasma of QCD matter, people were very, very excited because we got awfully close to that lower bound. Yes. So there is some insight that QCD is quite interesting, since or the Quark-Gluon Plasma is quite interesting because we are creating the system with a specific shear viscosity that is about as low as you can possibly get theoretically.
Okay, thank you. Any other questions? Okay, I think I don't see any other questions. So I just want to remind our next colloquium will be September 9th. And that will be by Gotcha Bashar. So it'll be a UNC speaker. And Josh, I don't know, do you have anything you want to say to wrap up and maybe wrap this up?
Just maybe that people should go out and get some cookies and have a treat, as we usually do after a colloquium. It's great to be off to a good start this year. I look forward to seeing everybody again in 2 weeks.
Thank you, Josh.